Okay, let's go ahead and get started. Welcome everyone to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology fueled by our decades of research. So, at GIA, we consider ourselves so fortunate to be able to study and learn from gems. And it's our mission to share our discoveries and our learnings with the world. So I'm really excited to kick things off today. I'm Kelly Giordano, a member of the content team here at GIA. And I'm joined by Dr. Aaron Palke, GIA research scientist, and he's going to give us a behind-the-scenes tour of the analytical equipment we use at GIA for analysis and identification. So before we get started, just a bit of housekeeping. Everyone attending this is automatically muted. So if you have a question, please submit it using the Q&A feature you'll see at the bottom of your screen. Feel free to ask questions as we go, and there will be a Q&A session at the end where Dr. Palke will have the opportunity to answer some of your questions. We'll also send a recording of the session to you later today, along with a survey, so we'd love to hear your feedback. And with that, I'm going to pass you over to Aaron.
Thanks for the introduction, Kelly. I'm actually really excited to be here today to talk about the tools of the trade that we use every day in the laboratory to look at the gemstones that everybody sends into us and to do the research that we're bringing to you guys. I think there's a lot of stuff that goes on behind the scenes that maybe a lot of people don't realize at first. And so I think this is going to be a lot of fun for everybody, and I hope you guys enjoy this. So I'm going to get started. So this first slide, I have to point out that I kind of shamelessly stole this first slide from my colleague Wim Vertriest. He gave a really great presentation at the 2018 GIA Symposium about field gemology. And he opened it up with this slide, and I liked it so much that and it really kind of frames this whole story really well. So I wanted to use it again, and actually he gave me permission to steal it from him. So there's no bad blood there. But basically, Wim's point with this was looking at the evolution of the gemological laboratory from when gemological laboratories first started. Back in the day, the question was, what is it? What are you looking at? And it was a question of identification. So is it a diamond or is it a zircon? And as the gem trade evolved, things started changing and we started seeing new things popping up. So the question then became, well, is this stone natural? For instance, is it lab grown or is it treated in some way? And then further on, as the years went by, the question eventually came up, especially with color stones, of origin. So where is the stone from? And this is kind of this was the lead into his talk about field gemology, because this question of origin almost necessitates the question of field gemology. But I think it also frames this discussion as well really well, because if we're talking about the analytical techniques we use in the laboratory, I think we can kind of look at the evolution of the gemological laboratories and try to get an idea of where we are today by looking at where we've been in the past. So the analytical techniques you would have used to look at these same questions, what is it? Is it natural? Where is it from? They've been guided by this whole evolution and complexity of the gem trade and the evolution of the complexity of the analytical techniques we have to throw at these questions. I know people don't usually like slides with a lot of text and words, but this is just an overview of some of the techniques we use that I'm going to talk about today. I've kind of broken it down into two different techniques. So there's classical analytical techniques, where we have standard gemological testing, refractometers, polariscopes, spectroscopes, and then you also have microscopic observations in this sort of in this category of classical techniques. So using a gemological microscope to understand something about the gemstones we're looking at. And then what's maybe more interesting for this audience might be the advanced analytical techniques we'll talk about. So spectroscopy and trace element chemistry. And I'm not going to say each of these things right now because we'll talk about them later, but just give you an overview of what we're going to be talking about. Now, with all of these techniques, this huge laundry list of things that we can use to study these gemstones, you have to face the question of, well, which technique do you need to answer the question that you're asking? And I think it kind of depends on what you see a gemstone being. So what is your perspective? What is your viewpoint of what a gemstone is? For instance, for identification questions, just determining what the gemstone is, oftentimes if you can consider the gemstone to be basically an optical device. So I'm calling this the optical approach. If you want to know if is your stone a zircon or a diamond or a ruby or a spinel, you can consider it to be an optical device where light enters the stone, interacts with the stone in some way, and you measure the interaction between the stone and the light to get an idea of what the stone is. As we start getting into more complex questions like lab-grown stones and treatments and origin, I would suggest that we have to consider more in-depth studies of the stone. So we would, for instance, for lab-grown and treated stones, we would question, well, look at the geological approach. So not only is this an optical device, how does light interact, but also how did this stone form within the earth, or how is it grown in a laboratory? And as you ask more complex questions, you need more information about the stone. You need to turn more into the stone and look more of the stone as a mineral or a crystal, and start really probing the mineral as on an atomic basis. And I think these three different kind of approaches align well with these three questions that we have: identification, lab-grown and treatments, and origin. So the first approach, the optical approach, basically, like I said, we're considering the stone to be an optical device, like a prism that diffracts light and spreads light out into its characteristic colors. Oftentimes, the gemstone can be seen in the same way. And so I'm using this as an example. So say someone hands you a red gemstone. You may have a gut feeling about what that stone is based on the color or the cut or just the general appearance of the stone. But as I'm pointing out here, you know, that red stone could be a garnet, a spinel, or a ruby. And if your gut instinct didn't give you the right answer, you may be making a costly mistake. So you need some better way to identify the stone that you're handed so that you can avoid potential mistakes. And standard gemological testing is really kind of the main way we would make this identification in the lab. And I guess I would say at this point, you know, I came to GIA and I came into the world of gemology after doing my PhD, and I was doing a PhD in mineralogy essentially. And so I'd been around a lot of advanced analytical techniques, a lot of advanced instrumentation. And so actually the one thing that really surprised me and struck me when I started at GIA, I was impressed by it, is all the standard gemological techniques that I'd never really thought about before. And all these optical techniques we were using, and really made the impression to me that the standard gemologist really knows a lot more about optical mineralogy than a lot of kind of geological students at the university. So for instance, you might identify those red gemstones by looking at the refractive index of the stone using a refractometer. You could look at the birefringence of a stone to look at the differences in the refractive indices. You could use a polariscope to determine the optic sign of the gemstone, and even looking at a spectroscope in order to look at the spectrum, how the light is being absorbed by the gemstone, in order to make identifications of these different stones. And while I'm not going to spend too much time on these kind of classical gemological techniques, because a lot of you guys probably know about these things already, but I would say at this point, what are the limitations of gemological testing? You know, why did we have to progress past these gemological tests in order to get more information? And I would use this picture as an example. So this is a picture of, on the left-hand side, a natural ruby, and on the right-hand side, a lab-grown ruby. You could use these standard gemological tests, and you would basically get the same answer for both stones. You would have the same refractive index in both cases, because in both cases it's a ruby, it's a chromium-bearing corundum. You would get the same uniaxial negative optic character. You would get the standard gravity, specific gravity of 4.00 in each case. And so, you know, when we started having to answer these questions about lab-grown stones and treatments and this sort of thing, it became obvious that we needed some different techniques to progress beyond these standard gemological techniques to answer these questions. And so I would also suggest that this is where we started to have to come to this geological approach. We had to start looking at gemstones not just as optical devices, but as geological specimens, as rocks that formed within the earth under certain specific geological conditions. And this approach really helped us to better answer these questions of, is the stone natural? So as an example, again, we have this specimen that I showed in the previous slide. It's a ruby in this rock, right? So it's a ruby in the rock that it formed in the earth millions of years ago. And this is actually, the rock that it's hosted in is called a marble. So it's a metamorphic rock composed mostly of calcite. And you find these in Myanmar and Vietnam and Tajikistan, Afghanistan. These marble-hosted rubies, you find them quite frequently. It's really one of the dominant forms of ruby within the earth. And so if you had a ruby, like this gemologist here on the right, looking in his microscope, if he was handed a ruby and he had to determine, is this a natural ruby or a lab-grown ruby? He could use his microscope to look inside the ruby for clues. And what he might see is this photomicrograph in the middle, at the middle bottom. What this photomicrograph shows are tiny inclusions of calcite. And so all of a sudden he can make this confident call that this is a natural ruby because he's seeing these inclusions of calcite, which makes him think about these ruby-hosted marbles that form within the earth in these rocks composed dominantly of calcite. And he might also see apatite inclusions, sulfide inclusions, other minerals that you also find in this type of a rock formation in the earth. Now you hand him another ruby, and he looks inside the ruby. He sees a photomicrograph as shown here in the middle at the bottom there. He sees curved bands, he sees gas bubbles, and all of a sudden he says, I've never seen a rock formation in the earth where you find completely circular rubies with gas bubbles in them. And so but then he says, oh, but they do form rubies in the laboratory. They grow them in these boules, these synthetic lab-grown rubies that have these cylindrical shapes to them. And so all of a sudden he can make this confident call that this is a lab-grown ruby based on the inclusions within the stone. So he took this geological approach to try to understand the formation conditions of these gemstones to get an idea of providing some information about what this stone actually is. Is it natural? And the same is true for a lot of other types of stones. Really, as you had all these different synthetic lab-grown stones coming into the gem trade throughout the 20th century, from emeralds to spinels to sapphires and all different kinds of gemstones that were being grown in the lab, it really became obvious that the gemological microscope was basically probably the most powerful tool we could use to identify these stones. So for emeralds, you could look at nailhead spicules and chevron growth patterns, these flux fingerprint patterns from the flux-grown emeralds with these high relief flux material occupying these fingerprints. And it's not only lab-grown stones that we're looking at, also you could look for treatments using this sort of, I would say, geological approach. So for instance, in an emerald, if you see some material filling the fractures, you can look for these blue flashes and for these residues filling the fractures in an emerald, you would say, geologically speaking, there's really no reason why an oil would seep into the fracture in the emerald. An oil with a similar refractive index of the emerald would fill up that fracture. It doesn't make sense from a geological perspective. So when you see these things in the stone in your microscope, you can obviously say, oh, this was an artificial treatment introduced by a man. This is not something you would see geologically. Same thing for rubies, for lead glass filled rubies. There's absolutely no reason in the earth where a lead glass would seep into the fractures of a ruby, just happening to clarify the ruby and improve its clarity. So looking in a gemological microscope with this approach of understanding the geology of these stones, we can identify these types of treatments quite easily. Same thing with blue sapphires. Heat treatment of blue sapphires, you often find naturally, you find rutile silk in these blue sapphires, which you can artificially heat these stones, dissolve that rutile back into the stone and producing a nice blue color. And again, this is just something we don't see naturally, geologically speaking, in these types of stones. And actually, a lot of this information, this geological approach, can be used for origin determination as well. And really, the beginnings of origin determination kind of had their roots in this geological approach as well. And as an example, this is actually a slide that the opening slide I stole from Wim. This is a slide I stole from myself, actually, from a previous talk about the research behind origin determination. And the point of this slide was, if you were to determine a ruby's origin 100 years ago, you probably had one of two choices. It was either a Burmese ruby or a Thai ruby. And you could do this from a geological perspective because these two types of rubies had very different geological formation conditions. So the Burmese ruby was formed in a marble in a metamorphic environment, whereas the Thai ruby was formed in more of an igneous environment, and it was transported to the surface by these hot basaltic volcanic events. And so the inclusions we see in these two types of stones are drastically different because the geological conditions of formation were drastically different. But as time progressed, we started finding new deposits of rubies and other types of gemstones from all around the world. And this sort of exposed a little bit of the limitations in this geological approach for origin determination. So for instance, Vietnamese rubies were found as well, and they were formed in marbles as well. So these rubies oftentimes would have similar characteristics as the Burmese rubies. And so all of a sudden, in some cases, you might not be able to use the gemological microscope on its own in order to make an origin call, because the inclusions in these two types of stones could be very similar. Similar thing with sapphires. A classic example is Sri Lankan sapphires versus Madagascar sapphires. And while these two localities are geographically distinct today, more than 500 million years ago when they formed, these Sri Lanka and Madagascar were actually smacked right up against each other when East and West Gondwana collided and formed these gemstones. Sri Lanka and Madagascar were geographic neighbors this time. And so they formed it actually in very similar conditions geologically. And with the unfortunate situation that in some cases, the inclusions in Sri Lankan and Madagascar stones could be quite similar. Again, we see this with emeralds as well. Ethiopian emeralds, Zambian emeralds, Russian emeralds, Brazilian emeralds, they can all be quite difficult to identify and separate using just a gemological microscope. If you were to look at emeralds 100 years ago, you might have only had to consider Russia versus Colombia, for instance. But with all the new deposits we have to consider today, all of a sudden this geological approach starts to show its limitations in a lot of ways. And so I would suggest that it's at this point we had to really start taking more of an inward look into the gemstones, and where we had to start with a more of a mineralogical approach, where we're considering the gemstone to be not just an optical device, not just a geological specimen, but also a mineral or a crystal, and it's a composition of atoms. And if we start looking at it in this way, there's a lot more different techniques we can start throwing at these gemstones to get more information about them and to make better determinations about their origin in the laboratory. And so some of the approaches, we can break this down into basically spectroscopic analysis and chemical analysis. I'm going to start with some of the spectroscopy, because the spectroscopy is kind of really interesting. And it's one thing that people know a little bit about it in the trade, I think, but there's a lot of stuff that goes on behind the scenes that we'd like to kind of share with you today. So spectroscopy maybe is a little bit of a scary term, right? But spectroscopy just means the science of how matter interacts with electromagnetic radiation. And electromagnetic radiation is basically, it's visible light. So it's all the light that we see every day, from basically 380 nanometer wavelength to about 780 nanometer wavelength. But this visible light is actually the same phenomenon as X-rays and gamma rays and radio waves and infrared rays. This is all electromagnetic radiation. So spectroscopy can involve measuring how any of these types of electromagnetic radiation interact with the gemstones that we're studying. We'll start off with visible light, though, because the visible light is kind of one of the more interesting aspects of this. And so as an example, one thing we might try to measure with spectroscopy is when you take white light, so white light being visible light in a broad spectrum of all the different colors of visible light. If you take that white light with all those colors and shine it into a ruby, why is the light that is reflected from the ruby coming back out of the ruby, why is it red? And to answer that question, we use a tool we call a UV visible spectrometer. So a UV visible spectrometer is basically, it's a light source, as you can see on the bottom left here. It's a light source that comes into a dispersion device, so a prism or a diffraction grating, where you have that white light being split into all of its characteristic wavelengths, all of its characteristic colors. And you can move this dispersion device, and you can cause different wavelengths of light to enter your sample at a given time. And then you can cycle through all the different wavelengths of visible light going through your sample, and you can measure how much of that light is absorbed relative to how much light you would get through into the detector without the sample in the way. And really, as we measure basically from about 300 nanometers to about 1100 nanometers in a UV visible spectrometer, you can go a little lower and a little higher. So really, we call it a UV-VIS spectrometer, but it's kind of actually a UV visible near infrared spectrometer. And that's just more of a mouthful, because you can really measure into the near infrared as well. So here's the example. We take a colorless sapphire, which is shown here on the left. You shine white light into this colorless sapphire, and you get white light coming right back out of the sapphire. And the reason for this is contained in the crystal structure of this material. So we look at the crystal structure shown on the right. And one thing to note is sapphire or corundum is a trigonal mineral. So it has this threefold symmetry going through the structure, which you might be able to see if you look at this crystal structure on the right. But the crystal structure is composed of aluminum and oxygen atoms, shown as the blue and the red balls, respectively. The thing is, though, with aluminum and oxygen, they don't really interact with visible light at all. So if we were to collect a UV visible absorption spectrum of pure colorless corundum, this is what you would get. You would get a flat line across the entire wavelength range of the UV visible spectrometer. You wouldn't see any absorption from this stone at all. So why is ruby red then? So, and I think the answer is ruby needs chromium, right? So if we replace some of those aluminum atoms with chromium, all of a sudden these chromium atoms, they do interact with visible light. And so if we look at the absorption spectrum of ruby, which is corundum containing chromium, you see these big absorption peaks at about 400 nanometers and about 550 nanometers. And so what you also see is this is absorbing a lot of the light in the green, the blue, and the violet regions, and it's not absorbing very much light in the red region at all. And so we have basically what we call a transmission window. You absorb all of the green, blue, and violet light, you let all of the red light pass through the material, which causes this white light coming into the stone to be reflected back to you as red light. And you might also, you know, if you've looked at standard gemological techniques for these kinds of analyses, you've probably looked in the spectroscope. You might have seen a similar pattern in the spectroscope as well. So if you're looking at a spectroscope, one actually interesting thing to point out is that a spectroscope is basically a UV visible spectrometer in a way. And you're looking at the same type of pattern in a spectroscope as you would get from an absorption spectrum in a UV-VIS spectrometer. We see another material. So you see, like in blue sapphires blue because of iron titanium pairs that are replacing the aluminum atoms in the structure. So when you have these iron titanium pairs next to each other in the structure, you have this absorption spectrum shown here, where you have a lot of absorption in the red and the green region at 580 nanometers beyond, but you're not absorbing very much light in the blue region. So what happens is you have this transmission window in the blue because of these iron titanium pairs, which are absorbing all of this red green light. Now that's really interesting, right? But it's not actually that big of a question for us in the Gem Lab, why a sapphire is blue or why a ruby is red. There's not a whole lot of practical information that we use on a day-to-day basis. A more interesting practical aspect of this would be looking at tourmalines, for instance. So blue tourmalines are colored blue by either the presence of iron, which is more common, or copper, which is a little less common. And so the copper variety of blue tourmaline is actually called Paraíba tourmaline, after the original locality it was found from in Brazil. Whereas the more common blue iron tourmaline would be called indicolite. Now the problem here for us in the Gem Lab is that there's a big difference in value between these copper blue tourmalines and the iron blue tourmalines. And one of the ways we have to identify these copper tourmalines is by proving that the blue color is actually caused by copper and not by iron. So we would do this with the UV visible spectrometer. We get to look at the absorption spectrum of a tourmaline and look for this characteristic copper absorption spectrum with one peak at about 720 nanometers and another one at about 900 nanometers, which you could contrast with a pure iron absorption spectrum with one peak at about 730 nanometers without that additional peak off further in the near infrared. So we use this technique, UV visible spectroscopy, every day in the lab to identify these copper bearing tourmalines so that we can more confidently identify these stones when we're issuing reports on them in the trade. Another good example is cobalt spinel. So cobalt spinel is spinel that's colored by the transition metal cobalt, of course, and it gives it this kind of classic cobalt blue color to the stones. This is an example shown here of a bright, vivid blue cobalt colored spinel. And we look at its spectrum. We would look for a cobalt contribution to the spectrum in order to be able to make this call confidently. And so if we look at the pure cobalt spinel spectrum, we can see that the absorption spectrum of this specific spinel is dominantly caused by cobalt, which gives us some confidence in making this cobalt spinel call. However, here's another example. This is another spinel which is not actually qualified as a cobalt spinel because it has a bit of a too dark of a color. It doesn't fall in that range of classic cobalt blue color. And so we would say this one is not a cobalt spinel. But if we look at its spectrum, we can actually see there's quite a bit of contribution from cobalt to this spectrum. And this is kind of where I'm kind of leading into the next set of techniques. We can start to see some sort of limitations to UV visible spectroscopy on its own. So while we can identify the presence or absence of cobalt in these two spinels, that alone can't really help us fully in making these cobalt spinel calls. Now, one thing I would point out, these are the two spectra of these two stones shown side by side. I'm showing also the chemistry of these two stones. So we have on the cobalt spinel, 46 parts per million cobalt, 10,000 parts per million iron. And so this terminology, parts per million, is a measure of concentration. So how much cobalt is in this stone? Basically what this means is that if you took 1 million atoms of this spinel, 46 of them would be cobalt and 10,000 of them would be iron. Now we could contrast with that with the spinel that was not cobalt spinel, the darker inky blue spinel. It had 39 parts per million cobalt and about 16,000 parts per million iron. So it had actually a similar concentration of cobalt, but it had way more iron in this stone. And it was this iron that was causing this inky dark blue color. Now, this sort of begs the question, though, is that, well, how do we measure these concentrations? How do I know that there's 46 parts per million cobalt in this one stone and 39 parts per million cobalt in the other stone? And this brings us to the next technique, this next set of techniques that we'll talk about, which involves trace element chemistry. So trace element chemistry measures not just the presence or absence of chemical impurities, but we can precisely measure their concentrations. So how much chromium is in a ruby, not just is there chromium in that ruby or not. And so this UV-VIS spectroscopy is really good for telling qualitatively what's in the stone. But for gemstones, UV-VIS spectroscopy is not great for identifying concentrations of these types of chemical impurities. Now, the first technique we would talk about, which was kind of the first one that was introduced into the laboratory, is X-ray fluorescence. A little bit behind the theory of X-ray fluorescence, this is a diagram of an atom here. It's a schematic diagram, obviously, but it gives the basic structure of an atom with the nucleus at its core. The little circle in the middle that says N, that's the nucleus of the atom, where the protons and the neutrons are held. It's a positively charged part of the atom with all of these negatively charged electrons buzzing around outside of the nucleus. And what is shown here in this diagram is also are the different levels that the electrons can go into. So we have all these different levels from electrons close to the nucleus to higher up, further away from the nucleus. And these are actually also correspond to different energy levels. So the further you get from the nucleus, the higher the energy that electron is. And we take advantage of this with X-ray fluorescence by actually shooting an X-ray at the atom that we're looking at the material we're looking at. And the atoms within that material, when the X-ray hits those atoms, it can sometimes dislodge an electron from an inner shell of the atom. It can send that electron flying and it'll exit the atom. Now this causes an instability, and one of these higher energy electrons will have to fall down to fill in that hole that's left where that electron was bumped out. And when this high energy electron falls to a low energy level, it has to do something to get rid of that energy. And so what it does is that it actually emits an X-ray of its own. And the way this technique works is that each atom has its own characteristic set of frequencies at which these X-rays are emitted when you hit that atom with an X-ray of its own. And so here's an example. So we have, this is an example of an output you would get from an X-ray fluorescence instrument. You would have these peaks at different discrete energy levels. And we know, because we've measured these things for tens of years, we know that these different atoms within the materials have their own characteristic patterns of X-rays that are emitted at different energies. And so what you see here is we can basically fingerprint this output from the X-ray fluorescence device, and we can identify which different elements are in there based on which peaks show up in the output, in the data. And this is actually an example of a lead glass filled ruby. So we see these very characteristic peaks that correspond to lead, which is Pb. And we see also some iron and some gallium, but this is actually one of the really good applications of X-ray fluorescence, is being able to identify lead glass-filled rubies by looking for these characteristic lead peaks in the data that we're getting from it. Here's a little bit of an overview of what the instrument looks like. So you put the instrument, your sample on the sample wheel shown here. You have an X-ray tube coming in at one angle. It's shooting your sample with X-rays at high energy. And then at the other angle coming off of it, you have a detector that's collecting all of the X-rays that are being emitted from your sample because of this X-ray that you're shooting at it. X-ray fluorescence is actually quite useful for some quantitative analyses. If you can take the emitted X-rays, the intensity of the emitted X-rays, and compare them to standard materials with known compositions, you can back calculate the concentration by looking at the intensity of your material and calculating the concentration of any certain element in that material. Some of the techniques, some of the applications for X-ray fluorescence are lead glass filled rubies. We can identify many laboratory grown stones by quantitatively looking at different chemical elements, looking for specific chemical fingerprints within those materials. X-ray fluorescence can be used to assist in some geographic origin calls. And it's really kind of a powerful technique that we can use to get an overview of the chemical composition of different materials, because it can basically look at elements from sodium all the way up to uranium. And it's also a non-destructive analysis. Here's another slide I stole from myself from that previous talk about origin determination. So again, if we were looking at Burmese rubies versus Thai rubies, the point I was trying to make here was you could use X-ray fluorescence as a tool to look at the iron concentration of those two rubies. 40 years ago, if those were the only two rubies you had to consider, this X-ray fluorescence device could give you an edge on identifying Mogok rubies versus Thai rubies. And here's what you would look for. So for a ruby from Myanmar, it would be a low iron ruby. You could look at it at an X-ray fluorescence pattern and look for the absence of any iron contribution in that ruby. Whereas for the Thai ruby, you would have a very prominent iron contribution because this stone was formed in a different geological environment in which iron was much more prevalent, and you could easily distinguish these two stones using X-ray fluorescence. Now, some of the limitations with X-ray fluorescence, though, is that elements lighter than sodium can't be detected. So, for instance, one of the big things in the laboratory right now are beryllium-diffused sapphires. You would not be able to identify beryllium-diffused corundum with an X-ray fluorescence device because beryllium is such a light element that it doesn't get detected very well using X-ray fluorescence. Another problem is that the sensitivity is not great with X-ray fluorescence for a lot of elements. You have relatively high detection limits for a lot of elements, usually greater than 10 parts per million, but oftentimes greater than hundreds, if not thousands of parts per million for some elements. Another aspect of this is that the interaction between X-rays and the materials we look at is quite complex. There's a lot of complex physics going on there. And in some cases, this makes quantitation difficult. So as time went on, we had these different challenges like beryllium diffused sapphires. We needed better data on our stones from our reference collection for origin determination. We started to look for another technique that we could use to get a little more information out of this. And this is where this device comes in. This is probably one of the most sophisticated instruments that we use in the lab. This is a laser ablation inductively coupled plasma mass spectrometer. Basically, there's two parts of this device. There's a laser ablation instrument on the right, and there's an ICP-MS, which is an inductively coupled plasma mass spectrometer on the right. And I'm going to walk through what this means, because that's just a bunch of gibberish, I'm sure, if you don't have any idea what those specific words mean. Basically, what happens in an LA-ICP-MS is that we use a laser, a deep UV laser, to remove a little bit of material from the girdle of a gemstone. And that's shown here in this photomicrograph on the right. These are small 50 micron pits in the girdle of a gemstone. You would never see this really unless you went looking at it in a microscope. But we can ablate a small amount of material from this gemstone and take this material, put it through the ICP-MS. So we put it into the inductively coupled plasma, which is just a really hot plasma like the surface of the sun, where the atoms that we've removed from the girdle of the gemstone are atomized. They're broken down into individual atoms, and then they're ionized. So that means we strip electrons from those atoms that go into this plasma. Now these ions are charged elements now. We send them through a magnet, a quadrupole magnet, we can separate the ions based on their mass, so, or how much they weigh. And so we can selectively filter out different elements based on their masses. And we can really get this full periodic table analysis. We can measure the entire periodic table from beryllium up to uranium and beyond in this one single analysis by tuning this magnet to separate these ions in the material based on their masses. Now I'm going to walk through that a little bit further as well. So this is kind of a schematic view that was put together by one of my other colleagues, Nick Sun. The analysis starts in the sample chamber where the laser is. So we take your sample, we focus a laser beam on the girdle of the stone, you fire onto the girdle, remove a small amount of material using the laser. That material is then passed into the plasma where you strip the atoms apart and then you strip electrons from the atoms and turn them into ions. Those ions then get sent into the magnet, the quadrupole magnet, and we tune the magnet very rapidly to filter out certain elements that we're not interested in, so that only the element we're interested in at that specific moment gets passed on to the detector. And so we measure the full periodic table at the detector by sweeping through this full mass range on the quadrupole. Now here's an example of what the data looks like. So this is a trace element plot for alexandrite. We started doing alexandrite origin services in last year. And one of the main techniques we use for it is laser ablation ICP-MS. What this plot shows here on the right is the concentration of our reference data from different known localities for stones with known provenance. So the iron versus gallium concentration of these reference stones. And we can use these elements like this in order to separate unknown stones. We can compare our stones sent in by our clients against this reference data to get an idea of where those stones may have come from. Now you can see there's actually some overlap in a lot of these localities. So for instance, Tanzania and Brazil, the blue and the orangey yellow spots overlap quite a lot in this plot. And similarly, the Russian and the Indian stones, the green and the dark orange stones, have quite a bit of overlap as well. So we wouldn't stop at just looking at these two elements at one time. We would look at the entire trace element profile of an alexandrite all at once in order to make these origin calls more efficiently and more accurately. And so here's a kind of an example of several plots we look at, from gallium to tin, to gallium versus iron, to magnesium versus gallium. And now all of a sudden you can see those overlap areas where we had, Brazil and Tanzania overlapping. We can get separation between those stones, and we can get separation between the Indian and the Russian stones as well. And so we do this with all the materials we look at. We have all these trace element fingerprints that we look for in these different materials. So we look at the entire trace element profile of the stone and compare it against the stones that we collected out in the field with known provenance in order to make origin calls in the lab. Another example is Paraiba tourmalines. So even though Paraiba tourmalines came originally from Paraiba in Brazil, we now found similar stones from Mozambique and Nigeria. So again, we can look at trace elements like copper, gallium, and lead. We use tin and zinc as well in making these origin calls. And we look at the entire trace element profile of these stones, and we can confidently make origin calls based on the data that we're getting from these laser ablation ICP-MS analyses. And one thing to note with this is we can get very low concentrations here. So the sensitivity of this technique is much better than for XRF. We can measure concentrations at less than 1 parts per million, oftentimes down to 1 part per trillion. So that means for every trillion atoms in these Paraiba tourmalines, we can often find 1 atom of lead, or 1 atom of strontium, or 1 atom of uranium. It's a very sensitive technique. We can measure very minute concentrations of a wide range of trace elements using this technique. Now, while trace element chemistry is kind of the main thing we do with laser ablation ICP-MS, we can also measure major element chemistry as well. And one application for this would be identifying different tourmaline species. So most gem tourmaline on the market is elbaite, but actually if you look at tourmaline mineralogically, it's this big family of different kinds of minerals, from lidocodite to elbaite to dravite and uvite. with slightly different chemistry in all these different mineralogical species. So we can use this technique, LA-ICP-MS, to measure the major element chemistry of these different tourmaline species and identify them in the lab. And actually this bracelet in the middle is a good example of that. This was a bracelet owned by Barbara Dutro, who is one of our colleagues. She's a professor of geology. And she had this, her specialty is tourmaline. She had this really nice bracelet that she wanted to help us with our research and help us look into this problem. So we analyzed every stone in that bracelet and found all the different tourmaline varieties in there, from dravite to elbite to lidocodite, and even a couple of citrines that happened to sneak into that bracelet, unfortunately. Another application is looking for laboratory-grown gemstones. So, you know, for emeralds, almost every emerald is pretty easy to identify laboratory-grown versus natural using a gemological microscope. There might be a few cases where the call might be a little more difficult and you need a little bit of additional information in order to provide some confidence in your call. So we can look at trace elements again, not only to identify the origin, the geographic origin of an emerald, but also to identify the laboratory-grown or natural nature of that gemstone. Now that's the trace element chemistry analysis. I'm gonna just finish off with a few more spectroscopic analyses that we use in the lab before taking some questions from you guys. So I'm gonna look at FTIR spectroscopy next. So like I said, with UV-VIS spectroscopy, we're looking mostly at this range of visible light that we are more familiar with, but we can also use spectroscopy to look at infrared rays, for instance. So rays that are at slightly lower energy than the visible light, at longer wavelengths than visible light. Here's an overview of the device we use. It's called an FTIR spectrometer. So FTIR stands for Fourier Transform Infrared Spectrometer. Basically, what you need to know is that you take an infrared light source, shine it through your sample using a variety of mirrors, and you detect basically the infrared light that's not absorbed by your sample. And so you can measure how much infrared light is absorbed at different wavelengths. And this can be used in many different applications for gemstone treatment identification and some laboratory versus natural stones as well. One really good example of this is low temperature heat treatment of Mozambican rubies. As Mozambican rubies have come to be a major player in the ruby trade in the last decade, people also realize that they could start heat treating these at low temperatures in order to improve the color, to remove a little bit of a bluish purplish component from some of these stones and give a better, brighter red color. Now, in some cases, you can look at the inclusions and identify this treatment. So the platelets you see in these Mozambican rubies might be a little bit altered by this low temperature heat treatment. But in some cases, actually, there's really no difference in the inclusions before and after heat treatment. So we realized we needed some other identification technique to find this type of low temperature heat treatment. And what we found was that FTIR spectroscopy actually is a very good technique for this. Now, in these lower wavelength, these lower energy regions where you measure in FTIR spectroscopy, you start to see more contributions from different species in the gemstone. So for instance, water that is dissolved in the gemstones often vibrates quite rapidly in these frequencies where you measure FTIR spectroscopy. You might also see oils that are filled in emeralds and that sort of thing. So in this case, what we found was that at this frequency of 3309 wave numbers, which is a little bit of an unusual designation of wavelength, but at 3309 wave numbers, in unheated stones, we might see one peak, but in the heated stones, we would often see these additional peaks at 3232 and 3185. And so if we identify these additional peaks related to water dissolved in the rubies, it's a good indication of heat treatment in these low temperature heated Mozambican stones. But some other applications are detection of laboratory grown stones like Alexandrite and assistance in treatment calls for some sapphires, heat treatments in some sapphires, looking at these different water peaks that represent water dissolved in the sapphires. Now the final technique I'll just end on is Raman spectroscopy. This is a picture of the Raman spectrometer. Basically what you do with this technique is you take your gemstone, you shine a laser on it with a specific wavelength of light, and then you measure all of the wavelengths of light that are scattered off of the gemstone in order to get some information about that stone. And basically what's going on with Raman spectroscopy is that when you shoot light on the gemstone, you're actually interacting with the vibrational frequencies of that gemstone. So gemstones vibrate at high frequencies, and when you shoot the stone with light, you can activate some of those vibrational modes and cause light to be scattered at very specific wavelengths. And the way this works is that each mineral basically has a unique spectral fingerprint of atomic vibrations. And so if we measure the frequencies of light that are scattered off of the gemstone, we can use it as an identification technique in order to match with known fingerprints of different minerals. Here's a good example. So, if we go back to that first red gemstone that we were handed at the beginning of the session, if you had to identify that stone, you could turn to standard gemological techniques. You could also use a Raman spectrometer though too. So all of these varieties of red gemstones would have their own unique fingerprint of vibrational frequencies in Raman spectrometer. And so we could quite confidently identify different types of gemstones using Raman spectroscopy. It's actually really good for identifying inclusions in gemstones as well. So this is an example of a fluid inclusion in an emerald, where you can identify calcite and carbon dioxide. You can identify the emerald host as well. And we can identify, this is more for maybe a geological experiment where you might be interested in what's the formation conditions of the gemstone. But it's very good for identifying inclusions within gemstones. And in some cases, this might be useful for making origin calls. You could look for amphibole crystals in Mozambican rubies. You could look for zircons and other amphiboles and different types of inclusions within different gemstones and try to trace those back to their origins based on what the minerals are within these gemstones by looking for their specific spectral fingerprint from the Raman spectrometer. And actually, that's kind of where I'm going to wrap this up a little bit. I hope you guys have enjoyed taking this kind of behind the scenes tour of the Gemological lab. Like I said, we do a variety of different things from the really almost simple but kind of sophisticated gemological techniques where you're considering the gemstone as an optical device to considering the gemstone as a geological specimen in order to get some information on what that stone is, if it's natural or if it's laboratory grown, all the way up to dissecting the gemstone at an atomic level in a mineralogical approach in order to get more information about origin and different kinds of treatments. So I'll leave it there. If you guys have any questions, I'd love to answer them and hear what you guys thought.
Oh, there are some good questions. So we'll go ahead and get right into it. Thanks, Aaron. That was all fantastic information. For the cobalt spinel versus non-cobalt spinel, where do we draw the line since they both have iron and cobalt?
Yeah, and so that's a really good question, actually. So in the laboratory, we basically use 3 lines of evidence to make cobalt color calls. The first is basically just the color of the stone. It has to fit within a certain range of colors that we expect for cobalt spinel. It has to have that bright, vivid blue color. If it's too dark or if it's too light in tone, or if the saturation of the blue color is too low, it's not going to qualify as a cobalt spinel. Now, we corroborate those calls with information from trace element chemistry and spectroscopy. So we look for cobalt concentrations, and we also look for the relative concentrations of cobalt and iron in these stones. And we look at the spectroscopy as well. So you have to have, the iron has its own kind of unique spectral contribution to the absorption spectrum. And so you look at the relative contributions of iron and cobalt in the absorption spectrum. And then we take all these 3 pieces of evidence together in order to make these separations between cobalt spinel and non-cobalt spinels.
Okay. With stones like the cobalt spinel, are there set ratios or ppm concentrations that you look for before making the decision as to whether or not you would even call it that?
We have guidelines for ourselves in the lab. And we always have some flexibility because there are a lot of different considerations that come into play when the color is determined for the spinel. So we keep loose guidelines for ourselves in terms of the cobalt concentration and what the spectrum should look like. But basically, every call is kind of a complicated call that has to take all these pieces of information together. So there's no kind of hard and fast rule for this necessarily. Basically, and this is kind of evolving a little bit as we go on and we learn more about these cobalt spinels. But at the moment, it's more of a holistic overview using all these 3 pieces of information without setting really strict guidelines about where is cobalt spinel and where it's not.
Okay. Is there a way to detect any type of diffusion using chemical analysis?
Yes, and that's a great question, actually. So this technique I talked about, laser ablation, inductively coupled plasma mass spectrometry. The only reason we have it in laboratory is that it's really good for identifying beryllium diffused sapphires. We use it a lot for origin these days because it's really good at helping us with origin calls. But the main reason we got it was in the early 2000s when beryllium diffused sapphires were hitting the market. We basically had no tool that could really identify that beryllium conclusively. And so we realized, we had XRF machines in the lab, but those tools couldn't identify beryllium. They couldn't measure beryllium because it's too light of an element. And so we realized we needed something better. And so this is where the laser ablation ICP-MS instrument came in the lab, basically in order to identify beryllium diffused sapphires. It can also help with identifying like titanium diffused sapphires and that sort of thing as well. But the main reason we have that is for beryllium diffused sapphires.
Okay. How many laser ablations do you have to do on a normal stone? And do you have to do one for each trace element search, or does one laser ablation allow you to search for multiple trace elements at once?
Yeah, so we typically run 3 spots on a stone, and each spot takes around 2 minutes. And so actually in that 2 minutes, we're separating that between taking a background with no material entering the plasma and the detector. And then we typically ablate on the gemstone for about 40 seconds. And in that 40 seconds, we're measuring the entire periodic table. So we're measuring every element all at once. And it typically goes in these sweeps of about 1 second. So every second, we're taking that magnet, the quadruple magnet, and we're sweeping it through different variables on the magnet in order to sweep through that entire trace element range from the light elements from beryllium all the way up to uranium in that 1 second. So we typically give about 40 sweeps of every trace element, 40 data points for every trace element in a typical analysis, but we get the entire periodic table all at once. And so we can see everything. We don't need to do separate measurements for different elements. We get the whole thing all at the same time.
Okay. How are gems cleaned to avoid contamination influences? Is there a special way that we have to do it?
How are they cleaned to avoid contamination?
Yes.
I guess it depends on what you're looking at, right? So if you're looking at spectroscopy, especially like FTIR spectroscopy, FTIR is very good at picking up oil and grease and these types of things. So that's why it's good for identifying like fillers in emeralds. But also, when you're handling the gemstone, you also have oils and greases on your fingers, right? So typically we use some very mild solvent. You might use isopropyl alcohol in order to get that oil off of the stone. For other techniques like laser ablation ICP-MS, it's not that big of a deal because we're actually ablating a little bit of material on the stone. And so if there's any contamination on the girdle, you'll typically ablate that material off before you start looking at the actual data coming out of the stone.
Okay.
We're very careful with cleaning stones. Some stones have durability issues, and so at most we might use some kind of mild solvent like isopropyl alcohol in order to clean a stone.
Okay, great. So what exactly does heat treatment do to affect the natural stone? Does it actually affect the trace chemistry, or could it even ruin the natural stone somehow?
So this might be where we distinguish between diffusion and like standard heat treatment, right? So if you're introducing chemical elements to the stone, that's diffusion, and that's like beryllium diffusion or titanium diffusion, where you're putting some chemical element in there that wasn't in the stone already. Now with standard heat treatment, like for rubies and sapphires, you would not be adding anything to the gemstones. So you would take advantage of, like for instance, for blue sapphires, you'd take advantage of micro inclusions of rutile, which is titanium dioxide. And what happens is when you heat treat a blue sapphire, you're taking those micro inclusions of titanium and you're dissolving it back into the corundum lattice. And when you dissolve it into the corundum lattice, you have iron in the lattice, and that titanium that is dissolved in can pair up with the iron and cause this blue color. So you're changing the color dramatically, but you're not adding anything to the stone. You're sort of just changing the the state of the stone a little bit from its natural state. With things like low temperature heat treatments of Mozambique and rubies, you're just changing kind of the oxidation state and the atomic nature of the gemstone, again, without adding anything in there. In this case, you're removing some blue from the stone by breaking iron titanium pairs, either by oxidizing the iron or by removing iron and titanium on the crystal lattice so that they're no longer sitting on adjacent crystallographic sites.
Okay. Do we ever, when you go on your field gemology expeditions, do you ever bring any equipment or perform any of this analysis directly at the gem deposits?
Yeah, and that's a good question. And actually, you can't bring your laser ablation ICP-MS, you can't bring your XRF, right? But we do have to be careful out in the field because many people have talked about this before, but you will see synthetics and you will see treated stones out in the field when people are trying to sell you stones for your reference collection. So you do have to be careful. Typically, we'll bring some standard gemological equipment with us. You might bring a polariscope, you'll bring a loop, but the stuff we have in the field is generally pretty limited. So you have to be careful, and you have to kind of just use some of these standard gemological tools in order to give you an idea of what you're looking for.
Okay. Is there a specific technique to detect treatments that are used to make synthetic stones appear natural?
Yeah, so any laboratory grown stone is kind of intended to look like the natural counterpart, right? So if you're talking about synthetic laboratory grown stones that are fashioned to look like rough natural gemstones, then yeah, any of these techniques we talked about could be used. So you could use trace element chemistry. You could, if you can find some part of the stone where you can look into it for its inclusions, you could look at through a gemological microscope to get an idea of the inclusions in the stone. So basically all of these standard techniques we talked about today could be useful for that sort of a application.
Great. Okay, well, I think we're just about up on time. So thank you so much, Aaron.
Right.
And thank you everyone for joining us. This has been great information. If you have any other questions for Aaron or for GIA, just follow us on Instagram, Facebook, LinkedIn, and Twitter. And thanks again for joining us today, and join us again next week where we'll have another GIA Knowledge session for you.